talk a little bit about some of the problems that we're battling every day in our group, and I don't mean the fact that the flush doesn't work in the toilet. I mean quantum gravity. So quantum gravity is one of the longest unsolved problems in the history of physics, probably, if you count from the time that it was recognized as a problem. In a sense, Einstein struggled in vain with finding a completely unified theory of everything, in part because he thought quantum theory shouldn't have too much to do with it. And we're still struggling with this today, and many of us are using string theory as our best bet for making progress on that front. But string theory is a strange animal. It's this amazing theoretical structure that fell into our laps. It's the only thing that so far we found that actually consistently brings the quantum world together with the world of gravity, with the world of the very big and of the cosmos as a whole. But at the same time, we didn't discover it by thinking very hard about some deep principle. We simply discovered it as the only consistent story that we can so far write down on a piece of paper. Okay, that's pretty good. That's better than having none. But it means that our exploration of string theory is guided entirely by its own extremely beautiful and rigorous theoretical structure, and not the way that we used to do physics. We used to do physics by looking for patterns in nature, and then to try to make those patterns that perhaps didn't have to be there, to make them seem obvious from the point of view of some new, deeper theory that would explain why they had to be there. An example of that was how Einstein discovered general relativity. He realized that the fact that all bodies fall in the same way, that didn't have to be true. That seemed coincidental from the point of view of the theoretical structure he had available. And he elevated this to a principle called the equivalence principle that it was supposed to give him a hint about how to construct a new theory of gravity in which this apparently bizarre fact was automatically built in from the start. That's how we used to do physics, and there's still some of that in how we do quantum gravity today. And I think the holographic principle is a prime example of that way of attacking the problem. The holographic principle is built on an observation that we've made over the last several years, that there is a connection between the geometry of space and time and its information content. A connection that didn't have to be there, and that seems impossible to explain except from the point of view of a more fundamental theory that incorporates both quantum mechanics and gravitation. Okay. And so we think that here again we've started to recognize a pattern that is giving us a hint about how to construct quantum gravity. Okay. And so what I want to tell you about today is a little bit about the line of thinking that goes into recognizing this pattern. Okay. So I want to start by asking an apparently rather dumb question, which is how many letters fit on a page? And the answer to that seems pretty obvious. It depends how large you write. So let's look at some experts, famous writers. Here's Kafka. He wrote too large. He wrote so large that at the end he needed to squeeze some stuff in really tiny letters here around the margins. Okay, so that's not so many letters on a page, but look at this guy. This guy's Robert Walser. He was a little bit, well, funny. And he started writing sort of the way Giacometti started making sculptures. He couldn't help himself but write smaller and smaller and smaller. These are actually supposed to be real letters. This is not some secret code. And you can read them, and people have struggled and transcribed all this stuff. And you can see that he fits a lot more letters on a page because he writes smaller. And he could probably do much better if he had just sharpened his pencil. Okay. And so we're starting to see that the answer, how many letters fit on a page, has something to do with how sharp a pencil you have available, right? You can't write arbitrarily small letters with a really blunt pencil. Okay, so this is a particularly sharp pencil. Here are a bunch of people who wrote words using individual atoms and then read them off with a scanning tunneling microscope. Okay. So these words are extremely tiny. Okay, we're talking nanometer scales. Okay. Maybe somebody in the audience can actually tell me what it says. So it becomes clearer and clearer that when we really, and you see where my question is going, right? I'm not asking how much can you really write on a page. I'm asking how much information content is there in nature, right? Think of letters as being individual constituents like these atoms. If I wanted to describe not maybe just a page, but say the state of this room in some detail, well, how much information do I have to give you to tell you exactly which state this room is in? To tell you where every atom is, what exactly is happening at every place? Okay. Well, again, that depends on the level of detail that I want to go to. Okay. So clearly what's happening in this room is changing from time to time, but let's not worry about that. For that we have good evolution laws that tell us, given an initial state, how things are going to look like a while later. What I'm asking about is how complicated is it actually to specify the initial state, the state of this room at one instant of time, to complete detail, so that you know absolutely everything there is to know about it. Okay. And you would expect that the answer to this question should depend on two things. Obviously, it should depend on the volume of the room. A bigger room should require more information to describe what's going on. And as this analogy with the letters on a piece of paper is hopefully illustrated, it clearly depends on what is the resolution we need to achieve. What are the smallest particles that are available? What are the smallest letters in which things are written in this room? Okay, so that's what you would expect. And it turns out that both of these statements are actually not correct. Okay, and the fact that they're not correct and the way in which they're corrected is probably telling us something about quantum gravity. So just to make the analogy completely clear, and please interrupt me now if it still isn't after this transparency. Here's an example. This is our room. And I'm going to neglect all the chairs and the people in the room, and I'm just going to focus on where actually a lot of the microscopic information is, which is in the movements of the individual little molecules of air that are filling this room. Okay. So these are lots of little molecules. If you work it out, unless I made a mistake, there are about 10 to the 28 air molecules in this room. So that's 1 with 28 zeros. It's a lot of air molecules. And in this analogy that I was developing, you should think of each one of these air molecules as encoding a little bit of information. Each one of them is like a letter. Okay, if say, we could say, let's call nitrogen moving to the left A, oxygen moving down B, and so on. Right? Clearly, we have more possibilities here than the number of letters in the alphabet, but the idea is just to recognize that the state of a system can be viewed as a paragraph full of letters, as a piece of information. Whether it's very useful or not so useful information, I'm not interested in here. Okay. So in this case, we had about 10 to the 28 letters. There are lots of different words one can form with those. It's quite a complicated system. Okay. But I want to ask the question in a way that really assumes complete ignorance in the beginning about the state that the room is in. In other words, I want to assume nothing but the size of the room. Okay. In that case, it's possible that we have a lot. Sorry, it says but suppose that. In that case, it looks like we actually, 10 to the 28 is a vast underestimate of the possible complexity of this room. Right? Clearly, we could fit more than 10 to the 28 air molecules or letters into this room, if we simply increase the pressure. Seal the room, squeeze a bit more air in, double the number of air molecules. Okay, triple it. Keep going. You can, it just means that they get the space between them is less, but you're squeezing more information in, right? Well, you can do that for a while, and then after a while, the air molecules will be so tightly packed up against each other that you can't treat this as a gas anymore. They're bumping up against each other, and so have you reached the limit here? Well, of course you haven't, right? Now we're just hitting the size of the molecule as a real limit, as something that limits our ability to write in smaller letters. So why don't we just break up these air molecules into individual atoms? Break up the atoms into nuclei and electrons. Break up the nuclei into even smaller things, protons and neutrons, and those we can break up into quarks. And you see that, it looks like there's just this sequence of smaller and smaller things that we can try to access and use to encode information. Okay. So you might think that fundamentally the world is an arbitrarily complicated place, that you never really know everything about the state that this room is in by just writing down a finite amount of information, because there's always some smaller scale where even smaller things are wiggling around and moving maybe this way or maybe that way, and you don't know because you had to cut it off somewhere. Okay. In fact, we like to describe the world using something called quantum field theory. That's very successful. It describes all the experiments that people have made so far at SLAC and other particle accelerators. And in field theory, there is actually no smallest scale. There's nothing that prevents you from... So a field is just basically a number that you assign to every point in space. And you can make little wiggles in a field. And those wiggles, just like a water wave, you can make those wiggles in quantum field theory arbitrarily small. So you can introduce little features in the field in the fields like the electromagnetic field that permeate this room, that you can introduce in arbitrarily small scales. So forget nuclei and quarks. There's no limit. You can get as small as you want in quantum field theory. And so strictly you would have to conclude that there's an infinite amount of information in any region of space. Okay. I'd actually like to stop for questions here and see if some confusions have come up.
So if it can be arbitrarily small, then what is the meaning of the Planck length, but smaller than the Planck length?
Good. So I haven't started talking about gravity yet. So the question was, where does the Planck length come into this game? To discuss the Planck length, you have to have gravity. You can't define what the Planck length is without involving Newton's constant. And I'm about to start involving gravity. Right? That's precisely the point. That so far, the way the story's been told hasn't involved gravity. Okay? We've done only quantum field theory. And usually when we talk about the very small, that tends to be enough. But it's not enough here. Yeah?
You also haven't talked about uncertainty. I mean, when you get to a small enough point, then you can't know what the state is anyway, so how much further can you get at that?
Very good. This is a perfect audience. You're just prompting my next points. So let's talk about the uncertainty principle. Good. What does the uncertainty principle tell us about a situation where we're trying to make arbitrarily small features in any system? Okay. The uncertainty principle is this famous recognition by Heisenberg that when you want to measure, say, the position of a particle to a given accuracy, you need to use light, say, of a short enough wavelength that the light wiggles are sensitive to this accuracy that you're trying to resolve. That's why we use electron microscopes to look at smaller distances than ordinary light microscopes. And that's why we build accelerators to look at even smaller distances. Okay. And the relation between the distance and the energy of the particles that we need to resolve that distance is one of inverse proportion. This is Planck's constant, and this is the speed of light, and never mind any of this. Okay. Let's just recognize that the uncertainty principle tells us here that the amount of energy that I need to build a feature of size delta x, this big, is inversely proportional to that size. So if I want to build a smaller feature, half the size, I need to use twice as much energy. Right? Or in our analogy, smaller letters are heavier, at least once you get really into the quantum world. It's obviously not true for the letters, hanging above shops and so on. But when you're talking about quantum-sized letters, then smaller letters are actually heavier than bigger ones. Okay. And why do I say heavier? I just told you that they have more energy. Well, remember that energy and mass are the same thing. Okay, that's one thing that we learned out of the many that we learned 100 years ago from Einstein. So let's apply this lesson that we just learned from the uncertainty principle. So far that doesn't look like a fundamental problem. It just means that the smaller the letters we use that we write the information with in this room, or the smaller of a resolution we want to read out, the more energy we have to put into the room. Okay? So one letter of size delta x has this energy. Well, this is how many letters there are in this room of this size. I just divide the volume of the room by delta x cubed, which is the size of the volume of one letter. Okay? That's how many letters I have, and I multiply that with the energy for each letter. That's the total amount of energy that I have in the room if I'm using this resolution to encode information. Okay? And notice that this blows up even more dramatically as I refine my resolution. It goes like 1 over the resolution to the 4th power. Okay? So you could still say at this point, so what? Right? So I just need to use a lot of energy. I didn't say that I was restricting the amount of energy that I'm allowed to use. Okay? The uncertainty principle doesn't tell you that, just by itself, that there's some smallest length scale that you can resolve. It just tells you that the smaller the length scale you want to resolve, the more energy you have to put in. Right? And so we see that a room with more and more information in it becomes more and more massive at a pretty dramatic rate. So now let's think about whether there's really something that imposes a cutoff on the amount of energy that we can have in the room. I didn't put this in by hand. I said we are just going to specify the size of the room to start with. I didn't say we're only going to allow up to this much mass to be in the room. But if we don't want to neglect the fact that there is gravity in nature, then gravity itself already places an upper limit on the amount of mass you can have in the room, just by specifying how large the room is. Okay. And the way that this works is as follows. Okay. If you increase the mass in a given volume, so you increase the density, what happens is that the gravitational attraction on the surface of this volume becomes greater and greater. Okay, we're familiar with this from, well, not personally, but clearly, the gravitational attraction of bodies of different masses is different. If you look at people hopping around on the moon, people walking around on the Earth. It also depends, of course, on the size of the object, how far away you are from the center. So let's keep that fixed. Let's put this room in outer space. Okay. And let's put an astronaut on the outside of the wall of the room. And there'll be a tiny gravitational force that attracts the astronaut to the center of the room because you're all sitting in the room. Okay, and you all have mass. Okay. And now if we start, instead of putting you into the room, start packing enormous densities of quark-gluon plasmas into this room, well, the mass is going to be dramatically larger than what it is right now. And this astronaut on the other side of the wall, floating with this room through outer space, is going to feel attracted more strongly to the room. Okay. And let's crank up the mass even further. It becomes harder and harder for this astronaut to just jump off into outer space without being pulled back to the surface of the room. Just like it's hard for us to jump off the surface of the Earth. Okay. We always get pulled back. Gravity always gets you in the end. Well, it doesn't always get you in the end. If you jump fast enough, then you can completely escape from the gravitational field of most bodies. Okay. And of course, there's nothing that's faster than the speed of light. Okay. So the problem is that if you crank up the density of the object high enough that even light isn't fast enough to escape from this object, then you've made what's called a black hole. Okay. And that can happen as we increase the mass of this room more and more. Black holes come in all sizes. They don't have to be gigantic astrophysical black holes. Black holes can be as small as this room. Okay. And if you've put as much mass as about 1,000 times the mass of the Earth into this room, which is a lot, but it's the principle that matters here. Okay. You just squeeze. Then you'll find that nothing can escape from this room anymore, no matter how fast it goes. Light can't even escape. You've made something called a black hole. And a black hole is basically a region of space-time that's separated from the rest by what you can think of as a sort of membrane called the horizon. It's a one-way membrane. If you cross this horizon into this strongly gravitating region, there's no way out. Okay. Of course, if you stay safely outside, there's no problem. You're fine. Okay. But now we realize that we can't simply assume that we can put as much mass as we want to into a room. So it's two things working together. It's the uncertainty principle, which is something that comes from quantum mechanics, which tells us that information costs energy, that writing things in small letters costs more energy than writing it in big letters. So it means that we have to put in a lot of energy if we want to put in a lot of information into this room. And we're combining that with a lesson from gravity, which is that you can't put as much energy as you want into a room. There's an upper limit. And putting those two things together tells us there is an upper limit on the amount of information that you can store in this room. Are there any questions about this? Yes? Maybe use the microphone.
You actually said that the room will become a black hole, and then you can add mass to the room. So what you're saying is that the room will grow because it's...
Yeah, that's an excellent question. So a black hole, that's right. Because black holes are in some ways very simple systems, we know exactly what happens to them when you try to add more mass to them. Okay. And what happens is that the black hole radius, the radius of this horizon, this one-way membrane, will grow in proportion to the mass that the black hole has. Okay, so the relationship between the radius and the mass of a black hole is very simple. G is Newton's constant, m is the mass of the black hole, r is the radius of this one-way membrane that we call the horizon. Okay. So if you now try to add more mass, you can't do that in a way that holds fixed the size of the region. And that was the one rule that we had in the game to start with. We want to specify the size of the region. Okay. You can't add mass to a black hole that's already as large as our room was without increasing the size of the black hole and thus violating the rules that we set to start with. We were asking how much information fits in a region of a given size. Okay.
That assumes you know the distribution of mass inside the image, right?
No, you see, that's the point. It doesn't. It doesn't. So the no-hair theorems that were alluded to in the introduction tell us that the way that a black hole looks from the outside is completely independent to in which order you threw things in and to what their consistency was. It settles very quickly down to a state that is characterized only by the mass of the stuff that you threw in.
From the outside, but inside there could still be a room and an empty space. I mean, that's how it looks from the outside, but inside there would still be this room and an empty space, right?
Well, yeah. So this is the first good question by the audience that is not supposed to be answered right away, but I can talk about this after I'm through with this line of argument. It's a very good point, and in fact, my contribution to the subject comes mainly from asking precisely this question. So let me already maybe rephrase the question. What if we don't care about what this looks like from the outside, but we follow the room in as it collapses inside this black hole? Okay. There seems to be some conflict there, because there it looks like we have a certain amount of information and it's just getting squeezed into a smaller and smaller volume as things collapse into a single point in the center of a black hole. But let's leave that aside for now and do thermodynamics the way we usually do it. We specify some rules and we stay outside the system and look at it from the outside. So what I've told you right now is basically a qualitative argument. Putting together quantum mechanics, the fact that small resolution costs more energy, and gravity, the fact that in a given volume you can have only so much mass, no more than the mass of a black hole that would occupy that same volume. Then from this we learned that there's some kind of cutoff on the amount of information. But we haven't learned what is that cutoff. And it would seem that, again, if you operate naively and you just try to do many different examples, that it would depend on precisely which system you're studying. We could put a gas inside this room and crank up the temperature until it collapses to a black hole, and ask what is the entropy, which is really the technical phrase for this information content that I'm talking about here. What is the entropy of the gas just before this collapse occurs, when I've maxed out the mass? I get one answer. And then I could fill this room with, I don't know, a bunch of elephants and squeeze them together more and more, and I'd get a different answer. Right? It's not clear that there is a universal answer that's simple and elegant and is telling us anything deep. Okay. But actually, precisely the same mechanism that tells us that there is quantitatively a cutoff on the amount of information that we can have is also giving us a hint about, qualitatively, is also giving us a hint about the quantity of information we can at most expect to store in a region. And that kind of statement is a very interesting statement if it's really general and it doesn't depend on the kind of systems that we're assuming live in the region, because it's telling us something about the complexity of nature at the most fundamental level, independently of whether we're talking about elephants or quarks. And so now let me use probably the one thing that we know best so far about quantum gravity. Quantum gravity is still a difficult subject. We know how to do a lot of things in string theory, but we don't know very well, for example, how to do cosmology yet from a quantum point of view. One thing we do know, thanks to some developments in the 70s, is the information content of an actual black hole. Okay. And this is, again, from the point of view of the outside. What we learned in the 70s is that a black hole has information in the same sense that this room contains information, the sense that we've been discussing all along. In this room, it corresponds to molecules moving this way or that way. In a black hole, we don't quite know actually what exactly it corresponds to, except in a few special cases where string theory tells us. But we do know, pretty much for sure, as well as we know anything in this subject, that a black hole really should be assigned an information content. And we know that this information content is given by the surface area of this famous one-way membrane, the horizon of the black hole. Okay. So a big black hole contains more information than a small black hole. That's not so unusual. What's a little bit unusual is that the information content of this object grows not in proportion to its volume, but to its area. And by the way, the volume of a black hole isn't terribly well defined in the first place. So it's a good thing that it grows like something that we actually know how to define. Okay. Maybe let me say a few words, since I'm pretty good with time, about how people came up with this idea that black holes have an information content, that black holes have entropy, as we like to say. Okay. The way that Jacob Bekenstein, as a graduate student, came up with this was to ask the question, can we violate the famous second law of thermodynamics by throwing something into a black hole? Okay. So the second law of thermodynamics tells us that in any physical process where we throw two systems together, or no matter what we do, the complexity of the final result is always greater than what we started with, the so-called entropy of it, the amount of things I have to specify to describe which exact state it's in. It's always greater than what I started with. It's like if I had all the gas in this room concentrated in one little corner and then I removed the wall that kept it there. I've gone from a very simple state, comparatively speaking, to a very complicated one, where each of the molecules has many more different positions where it could be. Okay. But it seems like if I take this entire room and throw it into a big black hole, I've made the world a lot simpler. Right. I'd let you go first. But if you then throw the entire atmosphere of this room and the walls into the black hole, it looks like I've decreased the complexity of the total system, black hole plus room. Because the black hole, as we just learned, is a very simple system. It's described by nothing but mass and maybe charge and angular momentum. But not these billions and gazillions of tiny little objects that move this way or that way. It's a very simple thing. It's just a membrane of a certain size. So I've taken all this complication and thrown it into this black hole, and now from the outside observer's point of view, life has become very simple. Now, if the second law of thermodynamics is worth anything, it should be valid for any observer, including the guy who stays outside the black hole. And that's what suggested to Bekenstein that there's an implicit assumption here that must be wrong, which is that the black hole itself has no complexity. Now, classically it has no complexity, but there's still room because it could have some complexity quantum mechanically in some quantum theory of gravity that we haven't discovered yet. And so by this indirect argument, we're learning something about this quantum theory of gravity that we want to discover. We're learning that when I throw something into a black hole, here's our room, that something should change in this black hole, and that change should make up for the lost entropy of the room. Now, Hawking had proved a theorem around the same time. This theorem stated that in any process involving black holes, the area of the horizon can only ever increase but not decrease. That sounds awfully like the second law of thermodynamics with entropy replaced by area. Okay. There aren't that many things in nature that can only ever increase. And so Bekenstein said very simply, well, let's just suppose that the entropy or information content of a black hole is equal to its area, measured in some suitable units that are constructed out of the Newton's constant that measures the strength of gravity and Planck's constant that tells us the size of a quantum. Okay. Now this quantity is supposed to be the entropy of a black hole. That was the new step. And it turns out that when you throw something into a black hole, the mass of the black hole grows, the radius of the horizon grows, therefore the area grows. And so there's something available that could have increased the total entropy, even though this information here was completely lost. Okay. As long as the area grows by enough to make up for the entropy that was lost when we threw this system into the black hole. Okay. Well, That was a pretty wild conjecture to start with, but it held up in so many different ways that now we're pretty convinced it must be true. If a system like a black hole has mass and it has entropy, you can show that it must also have temperature. And in a completely different way, a completely different line of argument, Hawking later discovered that black holes really radiate as if they had a temperature of precisely the value that is required by Bekenstein's conjecture that black holes also have entropy. Okay, so things started fitting together. Much later in string theory, for some special black holes, people were actually able to calculate what makes up for all this information content of a black hole in quantum gravity. What's underneath this smooth classical surface that looks like there's nothing that can wiggle around. And people calculated what is the entropy of a black hole, really starting from, just like we would starting from individual molecules in this room, they calculated it from individual constituents that quantum mechanically make up this black hole. And they came up exactly with the same answer as Bekenstein. So we believe pretty strongly by now that this is really true, that a black hole is a complex system with an information content equal to its surface area, measured in units of the Planck length squared. So you can imagine tiling this horizon with little Planck tiles. This Planck length is very short. It's about 10 to the minus 33 centimeters. It's, some finite length scale. Okay. And to describe the state of a black hole exactly, I could write little zeros and ones on these tiles. And the different states it can be in correspond to the different ways I can fill these tiles with zeros and ones. Very similar to the different states of this room, corresponding to different ways in which I send tiny little molecules moving this way or that way. Okay. Each tile is a letter. Okay. So now let's be confident. Let's believe that the area of the horizon really is the correct way to measure the entropy of a black hole. Too many things have already come together and worked out for this to be wrong. And let's go the other way now. Instead of wailing about the fact that the second law of thermodynamics is apparently violated when you don't assign an entropy to black holes, let's use the fact that black holes have this entropy and assume that the second law of thermodynamics is true, that entropy always increases, complexity always increases in any process. Well, then we can use that to learn something about the complexity of ordinary matter systems that we throw into a black hole or that we convert into a black hole. So let's just go back to our old picture of having this room floating somewhere in outer space and cramming more and more mass into it, increasing the information content in the room until we get to the point where the room suddenly collapses into a black hole. Let's do this in a way so that we make sure that the black hole has surface area no larger than the size of the initial room. Okay, so let's convert the room by adding more and more mass to it into a black hole of the same surface area. Let's not worry about rectangular versus spherical. Those are subtleties. Okay, it's a spherical room. Okay, and you can just think of that as just another one of these famous physical processes in which the complexity can only increase. The nice thing is that you know the final complexity. I've just told you we have a black hole at the end, and the number of letters it has is measured by the area of this surface, of this event horizon. Okay. And so the number of letters we needed to describe the system we started with has to be less than or equal to that by the second law. Okay. And so we know that the entropy in this room has to be less than or equal to the surface area of this room, which happens to be the same by arrangement as the surface area of the black hole that we made. At the end, we can just forget about having made this black hole. We could have made the black hole, and so it has to be true that the entropy in this room is less than the surface area of the walls. A black hole is just like any other object. It's basically a membrane that you can probe. And if you throw something at a black hole, then what you will notice is within a very short time as it approaches the horizon, absolutely no signal from that object that you threw in will have any chance of getting to you anymore. It'll go completely dark. Now if you go towards the black hole and you try to see how big is this thing now, you will really find that it's gotten bigger. When you send some probes there and you basically look at, how close can I get to this thing and still pull them back, still not have them cross the horizon and fall in, it really will be a bigger surface. You can calculate this. It's really true. Right? The thing that fell into the black hole has long gone. It's in the past. What you see now is simply a bigger object with no trace of the object that fell in. So those are calculations you can do. This is really true. There are bizarre ways of choosing coordinate systems which can sometimes make you believe something else. But any physical question that you ask, like if I go there and I look for the system, is it still there? The answer is no. You're not going to see anything there.
That packing information more tightly requires more energy. The equation you showed earlier, is it actually having the information or accessing the information that requires the energy? It seems that having large amounts of information simply sitting there but not being used would not require energy at all. That's the writing or reading that requires energy. That would be large energy.
So that's not right, because having the information means that you've made some features in your fields, for example, that are very sharp, where you make your, say, the electromagnetic field change over very short distances by a lot. Okay, and to do that, you had to put in some energy in the first place.
That's the writing process.
So it's already the writing process, yeah. Yeah.
But simply once the writing is done, then it can sit there for an arbitrary long time and not exchange energy.
If you haven't exceeded your energy max, yeah, and made a black hole. If I take this room and I have information to start with about 10 to the 28 molecules, and which way is this one moving and that one and the other one, right? That's a lot of information. And in the end, you're left with 3 numbers. Forget the 3 numbers. Compared to 10 to the 28, that's nothing, right? So it's true there's a tiny little bit left, but that's not enough. Even if just a few numbers went missing, we'd already have a conflict with the second law. But almost all of them go missing. So the Planck constant is not a length. So the relation that I wrote down is, it tells you the relation between the energy of a feature and its size.
Sorry, I mean Planck length.
Then the Planck, yeah. So the fact that you can't make features smaller than a Planck length is true, but it's not a strong enough statement compared to what I've been telling you. So for example, if you just try to make one feature, if you try to encode one bit of information, you could get it to be as small as about 1 Planck length. And if you tried smaller, you would instead be making a Planck-sized black hole, a tiny little black hole. But if you have many bits of information, then the point at which things start collapsing into a actually much bigger black hole is already at a lower density. Okay. That's because the mass of a black hole goes in proportion to its radius, not its radius cubed. So actually larger and larger black holes have lower and lower density that you require to make them. Okay. So if you have a lot of information, like the amount of information we have in this room, I couldn't even pack all of that to a density of 1 bit per Planck length. It would collapse earlier. Maybe I should continue. Well, I've already told you the story. By doing this little thought experiment of converting this room into a black hole of the same surface area, we're learning that the initial information must have been less than the final information content, which we know how to compute, that of the black hole. So it must have been less than the surface area. And so this is the sense in which the world can be thought of as a hologram. I'm guaranteed that I can completely specify the state that this room is in, down to the smallest detail you can imagine, by writing little letters, even just 1s and 0s, on the walls of this room at a density of about 1 per Planck area. 1 per such tile of length 10 to the minus 33 centimeters. That should be enough. Okay. That should tell you all that there is to say about physics in this room. And the funny thing about this conclusion is that we assume nothing in order to get to this conclusion. We assume nothing about what the degrees of freedom are that are actually fundamental to nature. We didn't assume that there are quarks or strings or whatnot. We just said there can be more of them than is allowed by black hole physics. So we're learning something very deep about nature from a very simple argument. That's something quite beautiful. We're also learning something that's a little counterintuitive. You would have expected that if I scale up the length of each of the three directions in this room, if I make it twice as wide, twice as high, twice as deep, that I should get eight times as much information as the maximum information content. The volume is multiplied by 8. Instead, what I'm learning here is that I only get 4 times as much. The area grows only like the square of the characteristic length. Okay. So somehow the world isn't as local as we might have thought it was. No, you would think that the information in the room should be proportional to the volume simply because it looks like I can change a molecule, its direction over here in the room. It shouldn't affect anything that goes on over there. I should be able to write my letters completely independently at each point in space. What we're learning here is that at some deeper level, once effects of gravity become very important, that's no longer true. The only reason why it seemed true to us is that we don't operate in an environment that's close to complete gravitational collapse. We're really, really, really far away from that. It seems to us obvious that the world is local for the same reason that it seemed to us obvious that space-time doesn't bend before Einstein told us that it does. Right. It's not in our regime of everyday experience. But apparently it must be true if we are to make sense of quantum gravity. Now, the deeper reason to see why it's true, that's very hard to see, right? When we actually check if this is true, come up with an example, calculate how much is the information in this or that system, compare it to its surface area. You can do that calculation over and over and over again. For many different systems, you always find the information that you had there is less than the surface area, if you take into account gravity properly. If you make sure that you haven't packed more density into the region than is allowed by the laws of gravity, than is allowed if we don't want to collapse to a black hole. So you can check many different examples, and the way that it works out is really quirky. It seems to be a bit different in each example. There's always some effect in that combines gravity and quantum mechanics that prevents you from putting too much information there. So this is very similar to how we understood the equivalence between gravitational and inertial mass before Einstein found the theory of general relativity. It seemed like a coincidental thing almost. Okay. And once he found the theory that underlies it, it became obvious. What we're looking for is a theory that makes it obvious to start with, that the number of degrees of freedom in nature has something to do with the area of surfaces and not with the volume. In some special instances, string theory has already succeeded in doing that in a very beautiful way. But this seems to be a pattern that goes far beyond the relatively simple spacetimes that we can currently study in string theory. So it may help us to move further. Now, what I've told you so far is a story where I've at least motivated this by some kind of Gedanken experiment, by using the second law. But in fact, the pattern that information content is related to surface areas is far, far more general than I had any right to assume based on this well, kind of very hand-waving argument I gave you. Okay, and that's where your question comes in. What if I actually follow something into a black hole? So I've cranked up the mass of this room very much, and now it's collapsing. And from the outside, it is a black hole. Nothing comes out anymore. It's just this region of space-time hidden away from us by this one-way membrane. But what if I jump in with the room? Or in other words, I just stay in the room as it collapses. Well, now what I'm seeing is that there's a fixed amount of information, presumably. Information can't decrease. which is getting squeezed more and more. Gravitational collapse looks like this. You basically get squeezed into zero volume. It's very simple. Okay. So we have a fixed amount of information that's collapsing into zero volume. It now looks like this statement is simply obviously untrue. The surface area of a collapsing room, if you just look at the walls, is going to go to zero. Its entropy content can't possibly go to zero. It can't become less complex as it goes to smaller values. That's the problem that I was worried about. I was worried about whether statements like this can make sense as apparently deep principles about quantum gravity if they look like they're simply untrue, especially in situations where gravity is extremely important, like inside a black hole. That would be a bad principle for quantum gravity if you can't make sense of it when gravity is strong. Okay. But it turns out you can make sense of it. You can invent a more precise statement relating area to area of space-time surfaces to adjacent space-time regions where you look at the entropy of the matter that's living there. That reduces to these statements that I've just kept giving you for situations where you haven't yet collapsed to a black hole. But that continues to be true deep inside a black hole. And the way that nature conspires to keep it true is even more bizarre and eclectic for different examples than the examples you could have studied in the regime that I was talking about. So let me just give you the short summary. What we've learned is that this pattern is more general than what I was able to present in this talk. To describe exactly what this pattern looks like, I would have to be more technical than I want to be in a talk like this. But the basic idea is very simple. You take a surface area, any surface, it doesn't even have to be a closed one like the wall of this room, and you look at light rays that emanate orthogonally away from the surface area. Imagine the walls of this room were lined with little laser guns, and they send light rays towards the center. And you look at what all these light rays see before they intersect. And that's what you count as the information content that you're going to compare to the initial area. Okay. Now, if we're just all sitting peacefully in this room with no gravitational collapse, that's exactly the same statement that I was making all along. The light rays simply see what's in the room, and that's what you count. Okay. But if the room is headed towards a singularity deep inside the black hole, for collapsing very rapidly, what actually happens is that the light rays that emanate from the surface area, which might now be very much smaller already because the room has collapsed, might be dangerously small, smaller than the total information content of the room. Those light rays don't have enough time left anymore to get all the way towards the center of the room before space and time and everything ends in this horrible singularity deep inside the black hole. Those light rays are just going to barely be able to scratch the surface of the room, and then boom, everything is over. Okay. This is something you can calculate. You don't have to believe me. Okay. And there are many other examples like that. If you just work it out explicitly, somehow the light rays, if you work with light rays relating information to areas, then you really have a completely general pattern that you can't understand just from the point of view of black holes, little thought experiments like this. It's a very overarching, mysterious pattern that I don't think we have even scratched the surface off in terms of understanding this from a deeper point of view. And I think once we have a proper quantum theory of gravity, it's going to make this pattern seem completely obvious, while until then it'll remain quite mysterious. Thank you.